Looks like we can start. Welcome back. It's now officially week number 7. So this is the penultimate week, which means the course is pretty much coming to its conclusion. We're at the end of chapter 5, dealing with the definite integral and indefinite integrals. We'll be looking into 2 more sections. And then after that, chapter 6, we'll just do as many sections as we can with our remaining time. This will be all about just applications of the definite integral. So that's where we're at so far. If we look a little bit further into the schedule, what will be going on the next week is we'll be having our final exam. The official day will be on Thursday of that week. So we won't hold class on that Thursday there. And we'll be reviewing for the final exam on the 4th and the 5th. I think I was circling the wrong date. And we'll have our official date for the final exam be on the 6th. And just to be as flexible as possible with everyone's schedule, I have the exam available early, and typically people will be scheduling it between the 3rd to the 6th, as well as up to the 7th as the very last day. So that's what we have going on so far for the schedule. We still have a couple sections to get through before we're at the very end. As far as the final exam goes, the final exam is going to be a comprehensive exam. It's a 2-hour exam as well. I'm not going to try to write an exam where you're writing for the full 2 hours. It's going to be about 15 questions. It's still just 1 page of notes, so you'll have to consolidate your notes that you've been using before. But a good strategy there is to go to your exam 1, exam 2, exam 3, see what notes you wrote down for those exams and what notes you really actually used, and use that to kind of consolidate to one master set of notes for the final exam. So that's pretty much what we have going on. We'll talk more and more about the final exam as we get closer to that date. But any questions or comments at all, folks, to start us out today? Okay. Well, last week, it was a pretty busy week. We defined what we meant by areas under a curve in section 5.1. In section 5.2, we finally defined the definite integral. This is this integral from a to b, f of x dx. But then the major thing, section 5.3 showed us the fast route to evaluating this integral without using the limit of Riemann sums. We just find an antiderivative, evaluate it from the upper bound, subtract the value from the lower bound, and that's the area under the curve. The net area, as f goes from a to b. So it can be any antiderivative whatsoever, which means we take the simplest antiderivative. But that's what section 5.4 is all about. If we want to use this fundamental theorem of calculus, we've got to come up with an antiderivative, and that alone is not always a very easy task. So that's where section 5.4 gets involved. Here we're looking into indefinite integrals, and all an indefinite integral is an antiderivative. So if we can find out tricks of the trade for coming up with antiderivatives, we'll see more tricks here in section 5.5. We'll be better able to use this fundamental theorem and more and more situations. So that's where the idea of the course is going so far. And if you know you're looking into taking Calculus 2, Calculus 2 is going to go essentially launching as you start on the very first day. It'll be section 7.1, integration by parts, which is the next thing you would do after the substitution rule. We're just doing some extra topics in the middle for applications of the definite integral itself. So we did just one of these. Let's take a look at them before we launch into the very next one. It's said to evaluate the integrals. This one's considered to be an indefinite integral because there's no integrate from a to b. There's an integral sign, but no lower limit or upper limit of integration. That means it's indefinite, and all we're trying to produce is the antiderivative, which means we always have an immediate check to our work here. If this is the right antiderivative, all we have to do is differentiate our answer in blue, and we must get the integrand in green. The derivative of hyperbolic cosine is in fact positive hyperbolic sine. That one doesn't flip to negative, like the derivative of cosine is negative sine. And the derivative of cosine at x is negative sine of x. The derivative of c, the constant of integration, goes to 0. So this is the most general antiderivative of the integrand, or the antiderivative just for short. So that's the one that we did before going off into the weekend. And what we'll be doing in these notes is just practicing doing more of the same. Really, this is section 4.9, just a complete do-over. But the main thing is we're just using a different notation, the indefinite integral sign. Any questions on the warm-up question or warm-up problem that we did before we go to the next question? Okay, here's where it gets a little bit more trickier in part B. Finding an antiderivative when things are being multiplied or divided can be really sketchy. The antiderivative of this is not the antiderivative of t cubed times the antiderivative of t minus 1 times the antiderivative of t plus 1. In fact, if we were trying to differentiate that, it wouldn't go that way either. You'd have to use a product rule. So to get the antiderivative of this to solve the indefinite integral, we need to expand this out, then do like we did in part A, find the antiderivative going term by term. So first thing we'll do is just a bit of careful algebra. Let's focus on this function here, just on its as its own problem, expanding it. We can rewrite that as t power 1/3 from the square root of t cubed that we saw. Hang on, let me take another quick look at that. This is a good review of exponential notation. That was a t power cubed. It's a square root, so this is t to the power of 3 halves, where the halves came from the square root sign. So probably good to look at these carefully before you just launch into it. So we get t power 3 halves. Then we're taking t minus 1 times t plus 1. That just becomes t squared minus 1. When we expand, we'll cancel the middle terms, and that's all we'll get. So this is still not good enough. We want to expand that even further. So let's rewrite this as t power 3 halves. Change the exponent on this one. We can write that as t power 4 halves minus 1. Distribute that t power 3 halves inside, and we'll get t to the power of 7 halves minus t to the power 3 halves. And that's the thing we really want to integrate. So we go back over here after our algebra, careful algebra, making sure that exponent came in just right. What we're really doing is solving the indefinite integral for t to the power 7 halves minus t to the power 3 halves dt. So now that we got it to this form, it's pretty much like part A. We can use a sum and difference rule. Just like with differentiating, find the antiderivative of a difference just means find the antiderivative of the first term minus the antiderivative of the second term. So we're ready to begin. This becomes, now when we do the antiderivative from section 4.9, the derivative makes the exponent go up by 1. So write in a little bit of extra space before you write the base t. Add 1 to 7 halves just means plus 2 over 2 to get 9 halves. Then we divide by 9 halves, which means multiply by the reciprocal 2/9. And that handles the very first term. So that's 1 down, copy the minus, give it a little bit of space, and do it all over again. But same idea, we're just taking 3 halves plus 1, adding because it's the antiderivative, so it's 3 halves plus 2 over 2. We're now 5 halves, then multiply by the reciprocal, which is dividing by that exponent. So minus 2/5 times t to the power 5 halves plus a constant. And at that stage, our work is 100% complete. The antiderivative is solved, and there's nothing further we have to do on that one. Any questions at all solving part B? Okay, well, that's our first one for the day. But what I would strongly encourage you to do, you won't lose credit if you don't do this. If you're really confident you have your right antiderivative, whether it's a homework problem or in an exam situation, then you get full credit right to this step. But if you have the extra time, say there's a little bit extra time on the exam, you're solving your homework and being really careful, here's something I strongly encourage you to do, at least on scratch paper, maybe on the margin. Do a check on this. What we have in blue is an antiderivative. That means if we differentiate the function in blue, we should get that integrand in green, which means we're just reusing all of our techniques from chapter 3. Whatever antiderivative comes up, differentiate it using those rules. 2/9 t to the power 9/2 minus 2/5 t to the power 5/2 plus a constant. Prime here to say differentiate. When we differentiate this, 9/2 is going to come down, multiply the 2/9. Now that we're differentiating, the powers go down. We always have to keep that direction really down pat in our mind. Think down for taking the derivative is a good way to keep it resolved. For antiderivatives, you do the opposite thing. Exponent goes up. So dropping that is subtracting 1, which means minus 2/2, so you get 7/2. Then go minus 2/5, and do it again. This t will have its exponent come down, so times 5/2. We'll subtract 2/2, so now it's 3/2. The derivative of that constant goes to 0, so we can go plus 0 or just ignore that last term. And you don't have to go too far because it's really just a check. We take as much steps up to the point that we're convinced. And because these fractions cancel like that, giving us t to the power 7/2 minus t to the power 3/2, which is that integrand there before we algebraically manipulated it. That's enough information for us to say the check was successful, and this is the right antiderivative. So if you have extra time, that's well worth the effort to just double check as you go. And that's how you might avoid making simple mistakes like forgetting that you had to expand this first. If you found the antiderivative in an erroneous way, but tried to differentiate your answer, you'd know, wait a minute, I'm way off. That's the reminder it had to be expanded first to this function before we even got started. Well, that's 2 down. We have several more to practice. But any questions getting through the main problem or the optional check? Okay, we won't do a check on every single one of these problems, but if we solve an integral here, whether it's a definite or indefinite one, and you're just curious about the check, don't hesitate to ask. I'm always happy to investigate further, show how the check might work. So let's try out our next one. Here, we're doing the antiderivative of secant theta times secant theta plus tangent theta, and same kind of idea. I don't know what the antiderivative even is for secant theta unless we work really hard or use methods from calculus 2. It's kind of a strange concept on its own. That's not an easy antiderivative. Same for tangent theta, the secant theta here. So it's kind of like the last problem. In the format that's currently in, this is like a huge bag of mysteries. But if we take the work to expand this, and in some cases possibly use trigonometric identities, all the mysteries you see here become a little bit more clear. So let's take another step and say this becomes equal to expand by distribute secant theta into the group. We get secant squared theta plus secant theta, tangent theta, d theta. And even though it looks way more complicated, secant squared theta plus a secant theta tangent theta, for our purposes, that's a simplified function. And here's the reason. Let's write down just some review derivatives from section 3.3. Feels like a long time ago. Section 3.3 told us that if you differentiate with respect to theta, the function tangent theta, you get secant squared theta. And if you've memorized these derivatives from section 3.3, good on you, because they're used so much, they become a part of pattern recognition, that having that already in the back of your mind of, aha, I knew where secant squared theta came from, it's that derivative, you have half the answer. Tangent theta is part of the antiderivative. And same idea, where did secant theta, tangent theta came up? So when you differentiated a secant theta, the derivative of secant theta from that section was secant theta times tangent theta. And so this is a good reminder for, say, the purposes of practicing reviewing for the final exam. These are great sections to go back, refresh yourself on those derivatives, and the more work you can put into memorizing these, the much more fluid and fast you can see and recognize what's going on with these current problems that we're in. So using those derivatives from section 3.3, here's the whole story to this one. The antiderivative of secant squared theta is tangent theta, plus antiderivative of secant theta times tangent theta is secant theta. Add the constant of integration, so now it's the most general antiderivative, and we're done right at that step. We didn't have to do anything more fancy than just expand secant theta in, so that we could see which functions we could recognize give us immediate antiderivatives. Well, our work is done on this one, and really over here on the right, that is the check. If you differentiate term to term, you get the things we expect. Any questions at all getting through part C? Okay, so really what's going on with section 5.4 is it's like a big review of section 4.9 antiderivatives, which on their own are a pretty big review of chapter 3, properties of derivatives themselves. Here's the next one. Part D doesn't look as friendly to the eye. There seems to be more going on with it. Let me hide that analogy down below. But it's kind of like what we did with our part B. On part B, before we even got started, we had to expand first. We'll do the same kind of thing here. We're just going to divide all terms by y squared, try to simplify this as much as we can. So let's start by taking the integrand here. This time I'll just work on the margin with this function on the right. The numerator could be rewritten as y power 1/2, for which we're dividing by y squared, minus y divided by y squared. And I didn't really set that exponent there, so let's just take an initial step. This becomes y power 1/2, and so we should write this one in the denominator as y to the power 4/2 to make the exponents compatible. Now this one you could rewrite as minus y to the power of -1, but that should always be avoided. Whenever a power -1 comes up, and this is the one and only exception, we should leave that just in the form 1 over y, so we can recognize the right antiderivative on that one. Then next step, simplifying these two right here, let's bring base y up into the numerator. This becomes y to the power of 1/2 minus 4/2, so -3/2. That one's okay. The power rule in reverse works just fine on that one. But 1 over y, like we mentioned before, should always be just written in that form. Let's go to the top of the notes to just emphasize why we took these particular steps algebraically. The very top of the notes, we have some great things, but I want to focus more on row 3 right here. Row 3 gives us two nice set of tools relevant to our current problem. For the very first term that we're going to deal with, we can use that power rule in reverse, or the power rule for antiderivatives. But notice it says it doesn't work when the exponent is -1. That's why we didn't bring the base y up into the numerator on this one. Writing it as y power -1 is just kind of asking for trouble almost. It's like trying to use this right here. But if the exponent's -1, we've divided by 0. We need to keep it in this format, 1 over x, or in our case, 1 over y, so we can recognize this is the exceptional case where the natural logarithm of the absolute value of whatever the variable is, y in our case, will come up. So using those two formulas, this becomes, take the antiderivative of y power -3/2 minus 1 over y dy. So when we integrate this as an indefinite integral, first, add a little bit of space, add 2 over 2 to this, that's the +1 part in the power rule above. So we'll get -1/2. We divide by that new exponent. That's what this denominator is all about. Divided by -1/2 is just multiplying by -2. It's reciprocal. And then that's the entire first term completed. Then from this one, we still carry the negative sign, do the antiderivative of a 1 over y, which by this rule right here is the natural log of the absolute value of y. And now we're done. We need the constant of integration for full credit, but don't forget the absolute value portion either. That's also required. We saw in section 5.3, one particular problem, why it really needed to have an absolute values. So let's write here just for a warning, because it's really easy to forget. Absolute value is required. So that's the conclusion on that one. And these are pretty much the type of problems that you're going to see in this section's homework assignment as well. A lot of these problems, you have to either divide or expand out. Expand on this one. Some of them are going to be ready to go, like say on the part A, we just need to find those antiderivatives and put them down on paper. But watch out again for the ones where you do have to do a bit of algebra. Pretty similar to section 3.2, where I think that was section 3.1 rather, before we had the product rule and quotient rule, we'd have done stuff with this algebraically, simplify like that, before we would have differentiated. Maybe write that as y power -1 if we're differentiating. Well, that's the whole set of antiderivatives for these notes. I do have an application that we're going to take a look into, a couple applications down below. But any last thoughts or questions on getting through any one of these? Okay, well, let's now take a look into, I guess this is really two kinds of applications we're going to look into. This one's kind of a routine math example. There's no real world application to it, but it's kind of an application in its own right. And then we'll look into the net change theorem, a more honest application. Our application will be to a quick problem in chemistry. But first, here's a good analogy that we kind of mentioned before, just in ordinary words, but I felt like it was a good idea to just put this down in paper. Integration, whether it's a definite integral or an indefinite integral, like our current section, is a pretty tough process. And this is a strong and accurate analogy. Differentiation, chapter 3, is pretty much like multiplying, where maybe this problem looks kind of tedious and miserable, 42,531 times 519, but we know the tools and the tricks to make that multiplication happen. Our hands might get a little bit tired, we might use a lot of paper, but it's straightforward, just sometimes tedious. And it's same with differentiation. You can put down any differentiable function, then you just decide, is this going to use product rule, quotient rule, chain rule, constant multiple rule, so on and so on. But once we know what rules we're using, it's a process that always gets us to right to a resolution. Now, integration is the weird one. Integration is kind of like trying to crack a code. It's not straightforward. And the analogy here is integration is kind of like factoring. Factoring is the reverse of multiplying. So that's nice because differentiation and integration, we saw a sense in which they are truly inverse processes. So integration is like factoring, and factoring in this kind of sense. Factor 2 to that power minus 1. 2 is not a factor of it because it's an odd number. It's not even, so we can't even get started by dividing by 2. Loads and loads of computational power have been leveraged at this one problem. In fact, encryption, keeping the internet secure so you can do online banking and all that kind of stuff, relies on the fact that this is still a really hard problem, factoring really large numbers like this one. And that's what integration is all about, really. It's kind of a code-breaking process in a certain sense. And we'll revisit this kind of idea with what we're doing in section 5.4 when we try to find more and more antiderivatives. So the reason for putting the analogy here on this point of the notes is, here's a really weird antiderivative. It turns out that the antiderivative of the natural log of x is x natural log x minus x plus a constant. And what question you might have is, how would you even come up with that? Who came up with that? That's a weird amalgamation of functions. Fact Calculus 2 will show how to do this one. It's a technique called integration by parts. But for the moment, what we'll do is just show it's true. So it's a random antiderivative. We've hinted at already before. Antiderivative of secant x is not straightforward either. That's a pretty tough problem on its own. But if we're going to prove something like this, that part's not so bad because we are differentiating, really. We just have to know what we're differentiating. So bringing it back to the organization for what an indefinite integral is, the indefinite integral of a function, natural log x, that's the integrand, is just the antiderivative. So if that's the antiderivative, what we should be able to do is differentiate the function in blue and get the integrand in green. And if that works out, your work is done. You've shown that this equation is true. So this is all we have to do in our proof. It's not so bad, even though it says the word to prove. Take x natural log x minus x plus a constant and differentiate. So now we're doing the differentiation. If we're differentiating this whole thing, the tools we're going to need are first the product rule. This is x times the natural log x. So when we work the product rule in the very first term, the derivative of that x there by the red dot is 1, and then copy natural log x. Go plus. Now copy that x where the red dot is. Move over, differentiate natural log x, which is going to be times 1 over x. So we've taken the derivative of the very first term. Now we're using the difference rule. The derivative of negative x is just a negative 1. Now we're using the sum rule. The derivative of a constant is 0, whether we're adding it or subtracting it. I'll go plus 0 just to show what happened to that constant, but it's not required. You can simplify down to here, just drop that part. Simplifying this further, we get natural log x plus 1 minus 1. And then when we go to the next step, we see that that's exactly natural log x. It's the integrand, and so this completes the proof. So if you can differentiate the answer, get the integrand, this is really just a check, like we mentioned at the start of our class today. You've shown that you have the correct answer to that antiderivative. So say here, this shows the equation is true. So strange antiderivative, you don't have to memorize this one. It's just a kind of an interesting problem all in its own. Any questions at all showing that proof there? Okay, here's where it becomes a kind of an application. It's really a mathematical application. If you differentiate something, then we have to think back. What is a derivative? It's the slope to the tangent line of a function. So if it says the equation above, referring to this one, we proved is true, means that the slope of the tangent line to y equals, we're filling in the blanks now, at x equals 1 is equal to something else. I think this is kind of a tricky problem personally. These are the kind of problems where I usually pause and think about it before I just launch into an answer. And here's a good way to kind of review as well as we go on this one. The derivative is defined in this way. We write as f prime, and whatever the derivative is, it's equal to the slope of the tangent line to the graph of the original function f of x at the point x, f of x. We have an x point. We just have to ask ourselves, what did we actually differentiate? We differentiated the function in blue, and the function in green was the derivative. So we got that as being the derivative of the function that's in blue. So that's what the f of x function is. The derivative of f, this would be the thing in green through this definition. So we can say that the equation above means that the slope to the tangent line to this function, y equals natural log x, at x equals 1 is equal to something. By going back to those notes, that something is just f prime at the value of x, where that value of x here is 1. So the f prime is natural log x. We just say natural log 1, which is 0 altogether. So that's tying the ideas together for finding an antiderivative, as well as going back to the slope of the tangent line. That's all the way back in chapter 2. So these problems become pretty tricky when you put those ideas together. But does that make sense to everyone on how we brought in natural log x as being the function that goes here? Okay, well, that's our first application we want to take a look into. We're going to take a look into one more question, and then we'll be in section 5.5, the last section that we'll cover in all of chapter 5. So chapter 5 is a really short chapter. Chapters seem to get shorter as we go in Calculus 1. And here's the last concept. The net change theorem. It's a interesting theorem. It's interesting in its name, really. Its format is also somewhat interesting as well. But when you think back to, say, the fundamental theorem of calculus part 2, section 5.3, look at this really carefully in view of the net change theorem, you realize they're saying the same thing. The net change theorem is just trying to emphasize its use in applications. This says that integrate f prime at x from f of b to f of a, and, or excuse me, integrate f prime of x from a to b, the answer is f of b minus f of a. So if you have a f of b here minus f of a, it means it's the antiderivative of this thing, f prime at x. We took off the derivative sign, so it's the antiderivative. And it's just worded in a different way in the fundamental theorem of calculus part 2. We just put in a lowercase f, but it's the same exact theorem, same exact idea, if you put f prime here. In fact, thinking in view of what we did in the very last question, if you differentiate that, that is the derivative of the function blue. So if you call this whole thing f of x, that's in fact just f prime at x. So that's all the net change theorem is really trying to say. It uses the fundamental theorem of calculus, and it just words it differently by putting in the derivative right there. So that's the derivative. This is the antiderivative evaluated at the limits of integration, b and a, so f of b minus f of a. So at its heart, even though it has this really fancy name, this is really nothing but fundamental theorem. Of calculus, part 2. So that, again, is always kind of curious that it seems to have this brand new name, which means it looks like it's a new concept, but it really isn't. Just a change in the notation for the way the integrand was expressed. But it gets that name whenever we use it in this kind of application, like we're going to solve down below. So that's what we're going to use it for. Any questions about the statement of the net change theorem itself before we get started? Okay, so here's a pretty simplistic scenario just to show a decent application to the fundamental theorem of calculus part 2, really, which we're calling the net change theorem. It says here, an athlete performs a 4-minute interval workout. It could be something awful like burpees, who knows what they're doing, but they made this athlete work out, maybe sprinting, and the rate of change of lactic acid concentration in their blood, I'm not sure how they measured this. Maybe they're taking lots of blood draws as the athlete's working out. That sounds terrible. But they have modeled the rate of change of lactic acid concentration in their blood measured in millimoles per liter per minute. So millimoles per liter per minute as a unit defined here. is given by this function. So maybe they had a lot of data points. Maybe they took a blood draw every 20 seconds using a machine. They connected the dots and they found that this is a good quadratic that showed the lactic acid concentration rate of change. So it's a rate of change, which means it's really a derivative. And that's why you see a C prime here. This is not the concentration of the lactic acid. It's the rate of change of the lactic acid. Said that wrong, lactic acid. They maybe did an initial blood draw and saw that the actual lactic acid, not its rate of change, was at 0 minutes, 2 millimoles per liter. And it's a 4-minute interval workout, so the time goes from 0 to 4. That's the only time this function is relevant. So that's the statement of the problem so far. It says find the lactic acid concentration, C of T. But if we're doing that, it becomes a section 4.9 problem, really. All we're doing is finding the antiderivative of C prime at T. It becomes a section 5.4 problem if we use an indefinite integral to express that antiderivative. And so that's all we're really doing in this problem. We can say C of T. Let's express this as an antiderivative. So indefinite integral, just a naked integral sign, no lower limit or upper limit of integration. Put in C prime of T, T squared minus 4T plus 3. dt. So once we have that integral, we can go from C prime down to its antiderivative over here by just using the ordinary rules. Here, power rule in reverse is going to give it a little bit of space. The new exponent is 3, so divide by it. 1/3 t cubed. Same idea over here. It's minus 4, but let's go minus t. Power is going to go up to a power 2. We know we're going to divide that 4 by that power 2. That would just give us a 2 in front. We can visually double check. If you differentiate that, 2 comes down, that becomes a -4. Power on t is a 1, giving us the right thing. Then we go plus 3. It's a constant. We just throw a variable t on it because the derivative of 3t is t. Our work isn't done. This next step is actually critical for this problem. This is why we always need the constant of integration, unless it's a definite integral. We go plus c. And now we have one more step where we'll use this initial condition, c at 0 is 2, to solve for c. You know, that looks like a conflict of notation when you think about it. I don't want to reuse c, which is meant to be the concentration of lactic acid, also used here. Let's use a different letter for our constant of integration. Let's use d, just so there's no conflict of notation between c, which is concentration, and that right there, which is meant to be a constant function. Let's put here constant of integration. Just a different letter this time because it was good just to keep our c's separated. So now that we have d there, we just need to solve for it using this initial condition. Any question getting the most general antiderivative first? Okay, so on the next step, I'll just copy this initial condition down for reference. C at 0 equals 2 would then imply we're plugging 0 everywhere t is. I'll write this in just so that we know where it came from. 1/3 0 cubed minus 2 times 0 squared plus 3 times 0 plus d is equal to 2. That's a fast equation, right? All of the terms in front of the constant of integration just are gone. So we get that d equals 2. We can substitute it back and say the concentration of lactic acid in this athlete is now 1/3 t cubed minus 2t squared plus 3t. Then it's plus d, which is 2. So we've got the lactic acid concentration function, C at t. C prime of t was just the rate of change. Actually, let's color code these a little bit better. C prime of t was the rate of change of the lactic acid concentration. But all we were really doing at its heart is redoing a 4.9 problem using the indefinite integral to express the antiderivative. So that completely solves part A. Any questions before we go to the next part? Okay, well, here's what the fundamental theorem of calculus part 2 gives us, or the net change theorem. We have that the concentration is exactly this function. And now if we want to know the change in the lactic acid concentration during this 4-minute interval, we can re-express it this way. The net change in lactic acid concentration is going to be the integral of from time 0 minutes to 4 minutes of the rate of change, C prime at t, dt. And it's a kind of a bold statement that the net change in the lactic acid concentration is this, which is fundamentally just an area. Well, we're about to solve the integral, but I just want to point out, we've done this already once before, something along these lines, when we were all the way back in section 5.1. In section 5.1, we had the velocity graph. But velocity is a rate of change. The unit was kilometers per hour on this. We want to find the net change of distance of this car. That's just the overall distance it went. And to do that, we had to find the area under this curve. We did it in a very methodical, painstaking way because we didn't know the function for v, and we certainly didn't know the fundamental theorem of calculus at this point either. But the area under this curve, which is just like this integral we're about to do here from 0 to 4, same exact idea. Find the area, and you'll get the distance. We just did it approximately. Same color coding, that's kind of an accident as well. The rate of change is here, rate of change is here. Find the area under that curve, and that's going to be either the net change in distance, or here, the net change in lactic acid concentration. So we mentioned before, areas can be essentially any applied problem whatsoever. That's because of the net change theorem. If a rate of change makes sense, then finding the area here, integrating the rate of change as a definite integral, also will make sense as a concept. Using the net change theorem, we can say that this whole thing is just equal to C at one value minus C at some other value. That'd be the concentration at the upper limit of integration, 4, minus the concentration at the lower limit of integration, 0. We happen to know C at 0 is 2, but we can see it really fast from our function we calculated here, C at t. So putting that all together, evaluate C at time 4, we would get 1/3. 4 cubed minus 2 times 4 squared plus 3 times 4 plus 2. Here's the minus part, minus concentration at time 0. That's minus just 2 if you use this equation above. And that's all we have to calculate for the overall concentration. There's a nice cancellation for free here. Those 2's are just gone. The rest, let's just throw into a calculator. So we're taking less time doing arithmetic, more time doing the calculus. This is 1/3. 4 cubed minus 2 times 4 squared plus 3 by 4, or it's probably easier to just type plus 12. And that's what we get, 1.3 repeating. If you like fractions, you can write that as 4/3. I'll leave that up to you. I'll write this as 4/3. And the unit on this one would be the millimoles per liter without the times minute. So that's our overall net change in the lactic acid concentration. It went up by this amount in the athlete's body. When we did it, that's the tour through the net change theorem. I believe it was a way for us to talk a little bit more about indefinite integrals in an applied problem, definite integrals as well, and just use the fundamental theorem of calculus part 2 once again. But any last thoughts or questions on getting through this applied problem here? Okay, well, we did it, folks. We're now on the last section of chapter 5, the substitution rule. So let's take a look into that one. Maybe just a couple reminders before we start to delve into this one. Major reason that we're doing this kind of work in section 5.4 was we're using the fundamental theorem of calculus. The major thing is to get the antiderivative f so that we can just actually use that fundamental theorem. Section 5.4 was about dealing with antiderivatives when we called it indefinite integrals. But essentially what we would like to do is reverse just about everything that we did in chapter 3 for the properties of our derivatives. And we did a lot of stuff. We know how to handle constant multiple rules, sum rules, and difference rules. Those go just about the same as before. The other rules go differently. The product rule is something we learn how to reverse in essence in calculus 2. And it turns out the chain rule is an easier rule to reverse than the product rule. That's a kind of a weird thought. But integration, again, we mentioned it's a weird process. So the rule that we will reverse so that we can get an antiderivative will be the chain rule. We call it the substitution rule when we do it in reverse. So here we're going to be practicing a chain rule quite a bit when we check our answers. And in a literal sense, we are reversing the chain rule. Hide a little bit about this. Oh, I should mention, I did make a quick revision before class today. Sorry about all revisions this semester. I felt like this problem was more interesting with the exponent of 5. It wasn't required, but it's a more interesting problem with that exponent. So that's the one and only revision on these notes. Should leave that there just for the moment. So for reversing the chain rule, here's where we go back to section 3.10. We mentioned when we were in that chapter, feels like a while ago already, a few weeks ago. In section 3.10, we dealt with linearization and one more weird concept which we named the differential of a function. The purpose for the differential is so that we can reverse the chain rule in the so-called substitution rule. So let's practice first how differentials go because it's our required concept. If you have a function defined in this way, y equals g at x, then the differential is this formal combination of symbols that we see down here. Y becomes a dy, and it's required to write down that dy when we did the differential. We made a big deal out of that in the lecture as well as the homework exercise instructions. The derivative of the function g goes here, but if the independent variable is x, we multiply it by a dx. Again, that's a required symbol as well whenever we're doing the differential. We'll see down below in the substitution rule how and why we needed those dy's and dx's following the same color coding we see down below here. But first, let's just practice taking a differential. So we have a quick function. The variable w equals tangent inverse q. This is a good reminder to take a look into section 3.6, where this is a nice table for derivatives, and any table for derivatives is also a table for antiderivatives. For dealing with tangent inverse, we don't mean reciprocal function, cotangent. We mean a literal inverse function, and its derivative goes like this, 1 over 1 plus x squared. So putting that all together, if we do the differential of this function w, we must start by writing down dw. And any instructions that say compute the differential must have that as part of a complete answer for full credit. Then we do the derivative of tangent inverse. That's just going to be 1 over 1 plus the variable squared, q squared in this case. And if the variable is q, we multiply the whole result by dq, following the structure we see above. So altogether, that's the full derivative of this function here. Weird thing about it was just the weird variables that was used. But sometimes we need weird variables. We have a variable u here. That's where u substitution gets its name. And so that's the use of the differential to get through the substitution rule. Well, we'll take a look in the substitution rule next, but any questions about just differentials in general? Okay, well, let's look into the substitution rule. Here's how the substitution rule is stated. We're integrating a function that's f of g at x times the derivative g prime at x. In order to do this kind of integral, and there's going to be lots of examples that we're going to see that follow this type of format, we start by taking something that's complicated about this whole thing. The reason an integral like this is complicated is because there's a function inside of the function f. That's kind of what's going on here in example 2. The function that would be f would be the power 5 function, but there's a function inside of it, this 1 plus 3x minus 7x squared. We have a function composition, so chain rules are going on here, which is what we're trying to reverse. So we take the thing that's complicated, that g of x, call it u, and then we form the differential. Du would be the derivative of g prime at x, times dx. And then we make a literal swap. This is a substitution rule in just the mathematical sense of substitution. G prime of x dx, we just rename as du. G of x, we called u in the first place. And so the whole integral just turns into integrate f at u du. We've changed the variable to u, so we have to undo that change when we solve this. That this, right where the red dot is, if we do the substitution rule just right, is often far and away the easier integral to solve than the original one. So let's practice immediately on example 2 and see how this formula goes. We have, again, a nasty looking integral that we're solving here. And it's not that we can't solve it with first principles. You can expand all this. And that's why I put the power 5 here. This is a practical problem where you wouldn't want to. It would just take too long, takes too much paper. It's a huge hassle to expand all that out. But if you can view it in terms of something like this that we see here, the problem is not as hard as it really had to be. So let's take a look at this again. There's a power 5 function, a function inside of it. But notice if you differentiate this function, 1 plus 3x minus 7x squared, you would get 3 minus 14x. That's exactly the function to the right here, which is what the substitution rule is trying to express. There's a function u inside of another function, and you're multiplying by the derivative of that function u, use differentials and the substitution rule to simplify your integral. So let's come back here and make that happen. So the idea is, here's the function u. U is equal to 1 plus 3x minus 7x squared. Once we have a function u, we wonder, what is the differential of that function? So that's our immediate next step to take. Compute the differential. The differential would be du equals, let's maybe scroll just a bit for some space. Take the derivative of the function on the right. The derivative of that function would be 3 minus 14x. And then we put in a dx to make it a full differential. And that's what this part of the notes is asking us to do. On homework and on exams, show these two pieces, what your function u is, what your differential is, and then when we come back here, we can start making substitutions. If we picked the function u just right, take a look at what that differential is. This is hopefully a piece of our original integral. And it absolutely is. That's the 3 minus 14x dx. That entire piece we can just rewrite as du right there. And this is just u to the power 5. So that's the substitution rule in its essence. We rewrite our integral. We're going to this next step here on the substitution rule as the integral of the function u. The function is the power 5 function that takes variable u. So this just becomes u to the power 5. And the entirety of 3 minus 14x dx, that's this equation, the differential. We just go from right to left, use the left-hand side. Another name for that whole thing is du. So effectively, that's what we've done. We've converted from something that looks really, really hard to do with nothing but first principles, hard in the sake of pure tedium to get through all of that. Expanding something to a power 5 as a trinomial is a lot of work. And then you still have to multiply it by a binomial, plenty of terms to find the antiderivative on, but all of it boils down to antiderivative of u power 5. The amount of reduction complexity there is staggering because that's just one fast rule from section 4.9 or 5.4. So let's pause here to kind of digest how we picked these things out. We picked u because the derivative of that function u is the 3 minus 14x. So that's the first thing we always try to look for in u substitution. Once we've picked u, we form the differential, and we just start literally doing mathematical substitutions. Replace the function here for u, replace everything else with du. Any questions at all getting through those steps? Okay, well, there's more to do. We still have to solve this thing. So the antiderivative of u power 5, power goes up by 1, it's power 6. We divide that by that power, so it's 1/6. This is an indefinite integral, so we do need a constant of integration. So we'll add c to that thing. And here's where we could still lose some credit, because if the original question was in the variable x, our answer must also be back in the variable x. So we just undo our substitution. Wherever u occurs in your antiderivative, look up what you said u was and substitute it back in. So this is going to be 1/6 of, here's our u, let's copy it in, 1 plus 3x minus 7x squared. It's all to power 6 at a constant. So at this stage, our work is 100% complete. There's no further steps we have to take on that. I think the preliminary work of finding u, taking its differential, doing the substitutions, those 3 steps are usually the trickiest. But if you can get to something that visually looks like it's easy to integrate, the last steps always go the same. Do the integral, undo the substitution, and your work is complete. Any questions at all, folks? Finalizing this one. Okay, well, like we mentioned before in the last section notes, this next part is optional, but especially when you're doing these as homework questions, I encourage you to check these as many times as you have the energy for. If you're doing homework and you skip a check on a few, I'm not going to take off any credit, even if you skip a check on all of them, same on exams. But the whole idea is to practice these techniques, and finding the antiderivative is just as important as taking the derivative. And so this is a good way to make sure you're on the right track. The check goes very fast, so it's always available to you. If there's extra time on an exam, do the check on the margin, and that would be a really great strategy. All you have to do for the check is take your answer, the whole thing, 1/6, 1 plus 3x minus 7x squared to power 6 plus a constant, and differentiate it. Forgot to say what we're doing. Let's put here, this is the check. Now, when you go to differentiate this, there's a constant multiple rule in effect because 1/6 is multiplying. Now, when we differentiate this function, that's the chain rule portion of the whole process here. So let's put here, just for the emphasis, that this requires chain rule. When you differentiate this as a chain rule problem, we first look for what function is inner. It's this one, 1 plus 3x minus 7x squared. The function that's outer is the power 6 function, so we differentiate it first. We go times 6. The new power is 5. We chain on a new derivative. A plus c, that will go to 0 when we differentiate, so that's just as well. I ran out of space. Go back to the inner function, put it in both the positions. 1 plus 3x minus 7x squared. If you put just the derivative down here, saving a step, I'd say good on you. You anticipated that next step. 1 plus 3x minus 7x squared. Then as we go to differentiate, the 6 and 1/6 cancel out. We're copying down to this stage. 1 plus 3x minus 7x squared to power 5. This derivative is 3 minus 14x. Feels like we've done that more than once because we really have. And this whole set of stuff here, this entire algebraic expression, is the original integrand. So that tells us our check is complete. We really did reverse the chain rule when we did u substitution. So if we reverse the chain rule, the check involves the chain rule like we saw here. Let's just put down for the notes. This is the chain rule. In reverse. So that's the whole punchline to the substitution rule. Sometimes what you're integrating is the result of something you differentiated through the chain rule, and u substitution just shows you how to reverse that entire chain rule. Those are the sequence of steps we would take. Well, our goal for these notes is to just practice this a whole lot more. This is one of those problems where you really just have to practice. So there's good problems to take a look at to practice on your own in the reading. Same for the homework exercises. On the notes, we'll do a set of indefinite integrals like these, where our whole job is to get the antiderivative. And then the last set of notes, we'll do another block of problems where they're all going to be definite integrals. So let's try out our next one, but any questions or comments first? Getting through the first one. Okay, well, here's our next adventure. Because it's so new, let's put down the substitution rule below as we go, so we can digest these steps as we take them in each new problem. First thing to note that we mentioned before is the format of this integral is kind of weird, but that's because algebraically dx acts as an ordinary symbol. So you can algebraically just rewrite this as 1 over 9x minus 4 times dx. Multiplying by a fraction will allow dx to multiply into the numerator. And so this is a way people sometimes write these. Textbooks write it that way to save a little bit of space. But for me personally, I like to visualize it that way. That's just easier for my brain to separate out the integrand, 1 over 9x minus 4, and the symbol dx. So now that we have that, the problem with this antiderivative is it's not the antiderivative of the numerator divided by the antiderivative of the denominator. Likewise, if you were to differentiate it, it's not the derivative of the top divided by the derivative of the denominator. That would require quotient rule. Well, we're not reversing quotient rule on these set of notes, so we need a different idea. And here's the idea we can take on this one. It'd be a lot easier as a problem if the whole thing was just, say, 1 over x. So the thing that made this function challenging is that entire denominator, 9x minus 4. But you can just take that whole thing, 9x minus 4, call it to u. If u is 9x minus 4, we can do its differential right away. Du would be equal to, take the derivative of 9x minus 4, that's going to be a 9, times dx. And this one looks a little bit different than the other one. When we did the one above, the 3 minus 14x dx matched exactly with what we had in the integrand, 3 minus 14x as a group. And so we just made a full swap on what we saw here. But it doesn't always go that way. Sometimes these get a little bit more messy. And so here's the next thing we can do. We have a u, we want to replace a du on this portion right here to simplify our integral. And this is just an ordinary mathematical equation where you can rearrange things to your heart's content. If there's no 9 here, you can multiply by 9 over 9. That's another route to take. Or the route our author usually takes is divide this equation by 9. You would get 1 over 9 du equals dx. And so now that entire dx can be replaced by this, 1 over 9 du as an entire function we'll do a swap on. It's a constant function times the symbol du, but we're allowed to do that as well. So we're still doing this same process in spirit. Du just happens to be rearranged through this equation. So that gets us started for our very first step. Now, when we go to make the substitution, we could rewrite it like this, integrate 1 divided by 9x minus 4, which we're calling u. So this is 1 over u. And then in the entire position where dx is, we're multiplying that by 1 over 9 du through this substitution we see here. And once we have that 1 over 9 is kind of a nuisance as a constant. But here's another great thing that you can do with these constants whenever they occur. If you don't like that constant being right there, you can go to section 5.2 and use this rule right here. Rule number 5 is a constant multiple rule for definite integrals and indefinite integrals at the same time. You can move a constant outside either a definite or an indefinite integral. So this 1/9, you could just throw right over here. 1/9 integrate 1 over u du. And more often than not, that's how the step would usually go from here to here. Once we know that we have a constant, we just move all the constants to the left so we can focus on the integrand and not get distracted by any kind of white noise in finding that right antiderivative. So this right here, following the arrow, is a common shortcut, often taken in the reading as well. And that means we're just about done. Finding the antiderivative of the original thing is kind of a tricky problem when you first look at it. But once we use the substitution rule that we see down below here, we're just finding the antiderivative of 1 over u, and that's not a bad antiderivative. It is a sketchy one. We do have to recall that the antiderivative of 1 over x is the natural log of the absolute value of x plus a constant. But aside from that, our work is essentially done. On the next step, go 1 over 9, natural log, absolute value of u, plus a constant. And the final thing that we have to do is just swap out what u was through the original substitution to return back to the variable x. Well, here's our last step then. Go 1/9, natural log absolute value of 9x minus 4 plus a constant. And that's the entire derivative, entire antiderivative of 1 over 9x minus 4 dx. Well, any last questions at all, folks? Getting through this one? Okay, that's a lot of steps on this one, but the more you stare at these kind of problems, the more you might have kind of cracked the code to the antiderivative of this one just by visual inspection. You notice you have a variable to power one in the denominator. It's a linear combination of that. That's an entire linear function. But the essence of this problem is really just this formula here to the right in purple. So if you guess that the answer should be the natural log of that entire denominator, you could have dropped right down to that step. Just don't forget the absolute values. But then you would have noticed that it doesn't quite work out like that, because when you differentiate your answer here where the red dot is, the chain rule is involved. The derivative of this places 9x minus 4 into a denominator, but then it multiplies by the derivative of 9x minus 4, which is a 9. That's why a 1/9 has to go in front to cancel that 9 that you get out from the chain rule. So this is the steps that we would take going at it from first principles. But the more and more you do these kinds of antiderivatives, particularly in a calculus 2 setting, when these kinds come up, oftentimes we do make the jump all the way to the bottom, discuss how the derivative of the chain rule would go. And so this is not an uncommon shortcut going here all the way down to here, but it's just mostly done in a calculus 2 setting. For calculus 1, practicing the substitution rule, not a bad idea to focus on how these steps go. Well, let's check out a couple more before we go into the next concept. Any last questions at all before we change gears to part C? Okay, so here's our next one to take a look into. And it looks pretty rough. There seems to be a lot going on with this one. This time we have natural log of x squared divided by x. And here's where the substitution rule turns into a bit of, I think our author likes to call this a bit of a art in coming up with the function u. That's kind of an uncomfortable thing to say. Usually we don't want to conflate math with art. We like to think of mathematics as there's a definite choice for u. It's going to work every single time, no matter what. There should even be a formula for coming up with u. But that's not actually how it goes. You can write down a problem like this where multiple different approaches are going to work. There's not always one way to do u substitution. There could be competing approaches. And there is no formula that tells you the definite way to pick u either. That's a bit of an art as well. The one guidance that I would look for is look for function compositions. Go back to the formula and see if you can find a function g side of a function f. And if you can find that, that's a great starting place. So in this integrand, there's a lot going on with it. There's a fraction here, but in the numerator, there's a power 2 function and an inner function, natural log x. The moment I spot an inner function, usually what I think in terms of is this might not work. It's not a guarantee, but it's a good place to start out. Let u equal that inner function, natural log x. If things work out according to the plan, if the differential allows us to substitute out g prime at x dx, whatever g prime might be, then we're on the right track. So once you pick your u, immediate next step is compute du. If u is natural log x, that implies du would be, take the derivative of natural log x, that's a 1 over x, multiply it by the symbol dx to make it a full-on differential, then look back at the integrand. You know, it's being divided by x, but that's the same as multiplying by 1 over x. So if you have an x in the denominator, there's a 1 over x in spirit there. dx is also there. So that tells us this substitution actually works as stated right here on paper. We do have a 1 over x dx. We'll replace that with a du. I think we usually keep that in green. So let me keep the color coding the same. Natural log x, we'll call u. It's just going to be written risen to a power 2. So this whole thing transforms into the new integral. Integrate. Here is our variable u to the power of 2. So that's how the numerator transforms. Just take natural log x, swap the u, square it. Then a 1 over x dx is what we're looking at really. That's just du by our differential formula. So we take this whole thing and multiply by du. So going from here to here, that's the role the differential plays. And now I think everyone would agree, the original integral looks horrible. Natural log x squared divided by x is a complicated function. But once we picked the right u, transformed it through the differential, this just reduces back down to a section 5.3 kind of problem. And a lot of work in Calculus 2 goes just like this. Do a number of tricks to try to bring this down to something like we've seen in section 5.3. Well, that's again, the substitution rule in a nutshell. There's always 2 more steps. Complete the antiderivative, undo the substitution. But any questions to this stage right here? Okay, well, here's the completion to the problem. We just take that. It's a nice, well-behaved function now. Use the power rule. This becomes 1/3 u cubed. So that's done. That's an antiderivative. Add the constant. It's now the most general antiderivative. Final thing, like we did all the rest, it's required for full credit is in any substitution, in any real math context, if you start with a variable, you have to return to that variable even after you complete the problem. Here we complete the problem of integration, but we still return to the variable x. So we rewrite this whole thing as 1/3 times natural log of x to the power 3, add a constant. And again, if we look at this through visual inspection, imagine differentiate that. You first would use the chain rule. 3 comes down, multiplies a third, and it cancels that. That would now be natural log x squared. But then you chain on a new derivative. You multiply it by the derivative of natural log x. That would be times 1 over x. And that's where this came into play. That's the 1 over x being multiplied in, forming the denominator. So that one's, again, pretty tedious in the sense that there's more than one way to pick a u, and not all picks for u are going to work. If you pick u equals x, it won't work on this one, in other words. Well, any questions before we try one more, the next challenge problem? Okay, well, here's part D, and it goes back to the analogy of integration, whether it's a definite integral or an indefinite integral like this one. It's kind of like trying to crack a code. The puzzle is, what did we have to differentiate to get that function? There isn't always a closed form answer, like we saw the section 5.3, Fundamental Theorem of Calculus Part 1. But this one does have an answer. It's just not always easy to spot these. Here's where we go back to section 3.6, where these derivatives start to really matter. We hinted at before that these are critical derivatives to memorize. So are the ones below. They're used all the time, calculus 1, 2, and 3. It's for the purpose of ease of computation. It's also for the purpose of pattern recognition. The colors that we used here were just to block out how some of these patterns work. And one thing we mentioned when we first looked at the derivatives of inverse trigonometric functions is, for some interesting reason, that comes up a lot. 1 over 1 plus x squared is a common function that just seems to reoccur. There's really, in essence, that function hidden inside of here. We just have to dig it out so we can bring in the right antiderivative. So the first thing we'll do to this is a little bit of algebra to see how the functions are going to come into play for that table we were just looking into. Let's rewrite this as e to the t one plus e to the power 2t. If we really want to make it fit in with this table over here, it'd be nice to have a power 2 written more in that explicit form. Also, when you see e to the power 2t, that's really a function composition. It's really just e to the power t squared. Wrong tab, there we go. Laws of exponents say those exponents multiply back to e to the power 2t. So there's really an inner function there. It's e to the t. And the derivative of e to the t is that other e to the t we see here in the numerator. Let me complete the symbols with the dt. That's starting to bug me. That needs to be there for correct integral notation. So if we can make that work, there's really a tangent inverse for the antiderivative on this one. Actually, let's just screenshot in these notes just as a reminder of their importance. Okay, that's a little bit easier than just clicking on that tab each time. So here's the thought on this one. There is a true function composition, but it's really tricky to see. So this is a pretty challenging problem in its own right. But if you pick a u equals e to the t, then you can take a nice differential. The differential is du equals the derivative of e to the t, which is e to the t. Because the variable is t this time, we multiply by dt. And I keep forgetting, with the color coding scheme, I want to keep this green on the left for du. And notice what does pop out on this one. E to the t dt does occur. Those are these components. They're really multiplied together. D to the t can multiply into the numerator. We just often leave it in this form. So this allows us to swap with a u here, divide by, hang on, let me think. I said swap with a u here, but rather this whole thing, sorry, let me backtrack my thoughts. This whole thing color-coded in blue just turns into a du on the right. That means there's really just going to be a 1 left over in the top over 1 plus u squared. So if we make that substitution happen, here's what it would look like. Integral of 1 over 1 plus u to power 2, and then du. Where these whole pieces right here really multiply together, they become e to the t dt, and they just transfer over to du when we make that substitution happen. So the numerator is now just a 1, e to the t we replace as a variable u, and now that we're looking at that, that's finally really this formula. Tangent inverse u is going to be used. If it's 1 over 1 plus x squared, antiderivative is tangent inverse x. But again, this is one of those hard ones where you could be left kind of scratching your head for a while and seeing how to crack the code on this. All the problems in the homework are solvable. So if you get stuck on any one of them, don't hesitate to ask, either in office hours, send a quick email, and I'm very happy of giving hints. Well, any questions at all, folks, on getting down to this stage right here? Okay, well, this is where the problem pretty much finalizes. Taking the antiderivative of that particular fraction, through pattern recognition, we recognize it as a tangent inverse process. So this turns into tangent inverse of not x. These symbols are important. It reminds us that the variable is actually u, so we throw in the variable u, add the constant. Then we return back to the original variable, same methodical step-by-step process as all the other ones. This turns into tangent inverse of u is really e to the t. Then add the constant c. And that's really bizarre when you look at that. It's hard to guess if you just saw this without going through the process, that this complicated combination of e to the t powers results in tangent inverse of e to the t plus a constant. But we've got it. That's the one and only antiderivative, really a whole family with the constant c. Any last questions or thoughts at all getting through any of these antiderivatives? Okay, well, this is the first half of the substitution rule notes. The good news with the next half is we're going to practice the substitution rule even more on the next ones. What we want to do is go from the indefinite integrals, like we saw in parts A through D, and put this to good use. The only reason we really care, well, not the only reason, but the major reason so far that we really care about these indefinite integrals is because they supply us with the antiderivative, which we can use in the fundamental theorem of calculus, part 2. So here is the substitution rule combined with the fundamental theorem of calculus, part 2. If we have that g is an inner function in a function composition, it's continuous on the closed interval from a to b, where the limits of integration are. F is continuous on the range of u. Let me put that down a line, equals g of x. That would be from g of a to g of b. Then the whole integral here, which is sometimes a pretty complicated looking integral, can be transformed into this one. I think we have enough time to practice one or two of these. And so when we come back on our Wednesday's class tomorrow, we'll start class by finalizing these notes, refreshing on the substitution rule. So still, we're really using the substitution rule. We're just extending now to definite integrals. We're finding the area under that particular curve. Well, let's show the process. It's pretty much the same formula, but notice one thing that does happen that is new. Let's maybe mention both things in one screenshot as an important set of concepts. Okay, one thing that's really weird when we go to the definite integral is we do not undo the substitution. And that's a pretty weird statement. So let's put down a really fast set of comments that ties both concepts together. For using the substitution rule here on an indefinite integral, for this problem, we must undo the substitution, which we just mean by that, return to variable x. But that must is always a strong word in mathematics. It's only for the indefinite integral. So if your integral is indefinite, we have to return to x. The must goes away if it's a definite integral. The reason for that is this is a dead-on equal. The value on the left is the area under a curve. It's not a function. It's not a family of functions. This is just an area. It's a definite number, positive, negative, or zero. And if you change to variable u, and you change your limits of integration appropriately, it's the same exact number. There is actually no need whatsoever to return to the variable x. And in some sense, that's a good thing. This shortens the process quite a bit. Whenever the book does these, especially in Calculus 2, where they get more involved, the book in a definite integral will often not return to the variable x whatsoever. They'll just solve the problem right here and call it good. So the concept I would make here is not required to return to the variable x. In other words, it's optional to undo the substitution. Our author, when you go through the reading, very often, I think pretty much exclusively, does not undo the substitution. And there's a very good reason for that. In Calculus 2, the problems get a little bit longer, and sometimes you make multiple substitutions. It's not unreasonable to do 3 substitutions in a single problem. There's ideas about U substitution, trigonometric substitution. It gets worse. There is inverse substitutions, and so on. And if you had to undo every single substitution at the end of the problem for a definite integral, it's just needlessly adding steps on. So when I go to solve this problem down below, I'll do it as the book does, not because it's required, it's just a best practice. It minimizes the work you really have to do on any said question, and it also streamlines how you'd be doing the problems in the reading as well. So that's always kind of jarring when we go from indefinite, where we always say you have to go back to the variable x, to now we're doing a definite integral. The answer is just an area, and we'll solve it here without undoing the substitution. So see this part of the notes just as a refresher on when and how and why to undo the substitutions. That was a lot of words for that concept. Any questions about that I can help clarify? Okay, well, let's give this one a try, see how it goes. First thing to note is there's a function inside a square root function. So that gives us a good idea that probably 4 minus x squared is a good choice of u on this one. Let's let that whole thing be u. So u equals 4 minus x squared. If that's our u, our differential du would become, this would be 4 goes to 0, negative x squared becomes a negative 2x dx. We do have an x dx, but we have an extraneous constant. The thing we typically do, like we did in the last block of problems, is divide out that constant. You can say negative 1/2 du is then just x dx. As we color code our integral, we see we've got all the right moving parts. Negative 1/2 is just going to move to the far left. This is the square root of u, x dx becomes that negative 1/2 du. But another thing that has to happen is we must change the limits of integration. So this is the next key step. This is the g of b, g of a portion right here, where u is the g function. So what we'll do next, let's just say it that way, use the g function. We'll start with the upper and lower limit of integration. We're going from x is 2. We usually say lower from higher. We're going from x is 0 to x is 2. If you know the value of x, you can just go here and substitute it in. If x is 2, u becomes 4 minus 2 squared, which is 0. And if x is 0, plug it in right here, u becomes 4 minus 0 squared, which is 4. So that's what the g of a, g of b is mentioning in those integral signs. And now the whole thing transforms over to this. Put a little bit of space before the integral sign. Copy the limits of integration in that exact order. Looks awkward, right? A larger number to a smaller number from 4 to 0 in that definite order, because 0 goes to 4 and 2 goes to 0. We can't swap those. Then we have a negative 1/2. We mentioned before, we often put that in front of the integral like that. The entire x dx that we see here, that's just the negative 1/2 du. So we throw in a du. Negative 1/2 is already out in front. And 4 minus x squared, that's just the variable u. It's square root of u, but that power we usually write in as 1/2. So that's really all we're integrating. The negative sign is not a big deal, but the limits of integration is awkward. But you know what? We can resolve that. We just go up to 5.2 and says, if you ever want to swap the limits of integration, you just multiply it by a negative sign. So if we swap these, we multiply by an extra negative sign, it just forces that to be positive. So you could rewrite this as 1/2 integrate from 0 to 4 u power 1/2 du. At this stage, we're pretty much done. We just go 1/2, give it a little bit of space. Antiderivative of power 1/2, we add 1, so 2/2, giving us 3/2. So we multiply by reciprocal 2/3. Then we take u to the power 3/2, now using the fundamental theorem of calculus, part 2, evaluate it from 0 to 4. So that's the antiderivative. We're going to do the evaluation just right here and now. Like we mentioned, there's no need to undo the substitution at all. If we did undo it, we'd get the right answer, but you have to use the original limits of integration 0 to 2 if you do undo the substitution. So on the next step, we cancel our 2's out. They're now gone. We get a 1/3. Plug 4 inside. This is 4 to the power of 3/2. Then go minus, plug 0. 0 to the power of 3/2. Then we just simplify from there. This is the square root of 4 to the power 3. When we square root it, we get 2 to the power 3. 2 to the power 3 is 8, so the whole thing just turns into 8/3, and that's where the problem would end, after simplifying from this stage on. Really, the tricky step is just to get to right here where the red dot is, actually more like right here. Then we just use properties of integrals to make it more appealing. 0 to 4 just looks more natural. And this was really just a section 5.3 problem at this stage, fundamental theorem of calculus part 2. So that's the full rundown. We'll practice 3 more when we come back on Wednesday's class to refresh on how all these go. But any last thoughts or questions at all, folks, getting through any one of these? Okay, well, this will be our stopping point for today. Like we mentioned, we'll finish off these notes when we come back next class. Then we'll start delving into our chapter 6. Our schedule says for chapter 6, we're covering 5 more sections, but we're not going to try to race through this. Chapter 6 is applications of integration. If we may not get to every single section, getting through section 5.5 is the major key to get us well placed for calculus 2. So everything that we can do that's a little bit extra, that'll just be for finalizing the course and really just extra practice on integration itself. Well, have a great night, folks. We'll be back to it, part B on our next class. Take care.